So now welcome again for the audience internationally and on YouTube. We're welcoming Alex Lubotzky to give the Distinguished Lecture Series at the University of Haifa. We should thank the Faculty of Natural Sciences and our chair, Anna Melnikov. And a few words about Alex. He's widely known in Israel. He got the Landau Award in '79, the Bergman Memorial Prize in '80, Erdős Prize in '90, a few other prizes, Rothschild Prize 2002, many other things. He's a member of the Israeli Academy of Sciences and Humanities, and he's a widely adored and respected researcher in Israel. And he's going to speak on high-dimensional expanders in math and computer science. So let's welcome Alex.
Thank you very much. It's a pleasure to be here again. Some of you may not know that I've been in this campus more than you think, because my son was a student here at the Chavaltzalot program. And even though he was very young, he was already married. As my wife said, he was married when he was 20 and a half. And my wife always wants to stress the half, that it was not. And he just started Chavaltzalot at that time. Before that, he was in a yeshiva, and then he was in Chavaltzalot, and he's still in the army now. Now he's a big shot. But I used to come to him also for Shabbatot. We spent Shabbats here on campus, but I guess not many of you had this experience to see how the campus is also lovely when it is essentially empty. Anyway, so it's given me a lot of good memories to be here again. Of course, I've been here a number of times as a mathematician. I want to talk today, and in these days, the general title I gave was high-dimensional expanders. They will go and come back, and my main goal is somehow to describe several topics which lies in the boundary between math and computer science. Or even more precisely, and maybe even more important, they're not really in the boundary in the sense some of them are really pure mathematics, some of them are computer science, but they are intrinsically related to each other. And sometimes in a slightly surprising way. So more than to give you really update and new results, I'll give some, but I want to stress the connection between the subject, even though they don't, to start with, they don't look so much connected. Now, something like 2 or 3 years ago, I gave here a talk about locally testable codes. That's something, an area within computer science. I'm sure everyone remember, including the notation, but still, I will repeat. I'll do it very shortly, because then I want to take the subject back to pure mathematics, like to show what the dealing with some computer science subjects, you can give you some insight towards some pure mathematical problem. So first of all, I don't want to assume anything. I don't know how many here from computer science, how many mathematicians. So so let me just recall very briefly what is the area of error correcting codes. So for us, error correcting code, the code will be a subset. I'll talk about linear code. So this is a subset, a subspace, a linear subspace of f2 to the n. The people will call it is NKD code. N is this dimension. K is the dimension of C. And D is the distance of the code, which is by definition the minimum of the Hamming distance between two different vectors in the code. Hamming distance is just the question, how many of them, in how many bits they differ from each other. Now, it's clear why we are interested in such a thing. We have a k bits of information. We want to send them over a noisy channel, and if you know there are mistakes along the way, so instead of sending k bit, you send n bits, and you want to the n bit, the legitimate one, those which belong to the code, to be of a good distance from each other, because then if there are few mistakes, you can correct them to the nearest code word. Of course, this is easier to say than to do, but there is a huge theory. If you want to know more, go to Noga. I will only give the classical. Okay, so now we are not engineers; we are mathematicians. So when I say a code, I don't mean a single code. I mean always that n is going to infinity. Even if I say a code, I really mean a family of code. So a code is called good. This is the definition going back to the father of modern information theory, Shannon, that C is good if there exists some epsilon such that what is called the rate k over n is more than epsilon, and also d over n, which usually denoted, I don't know, delta. People sometimes call it the normalized distance, or sometimes they call it the distance, already normalize it. So this is r and delta are both more than epsilon. So that they are both linear, the distance and k, the dimension are both linear in n. It's not at all clear that there are good codes when n goes to infinity. But nowadays, this is a standard argument that the theorem of Shannon was there exist good codes. Now, his proof was probabilistic. It says, okay, we want a subspace whose dimension is linear in n. So let's take that we take beta, random beta in f2 to the n, and we look at B perp, namely all the vectors alpha such that the scalar product, the inner product, I don't know how to call it, is equal 0, namely those in mode 2, right? You take sigma ai bi equal to 0. So this is a linear equation. Every such beta give you a linear equation, drop the dimension by 1, usually. And so let's say if I take 0.n random beta like that, I will get a subspace of dimension 0.7n at least, right? Because of simple linear algebra. And Shannon proved that with high probability, there exists epsilon, so that with high probability, independent of n, the distance, the normalized distance, will be bounded away from 0. And there is a lot of work about the connection with R and delta. It's clear that kind of R and delta compete with each other. If the dimension is very high, you cannot expect the distance to be very high, right? And vice versa. An easy inequality is that R plus delta is at most 1. But there is more sophisticated upper bound and lower bound, what we can achieve, what is the maximum we can achieve. Something goes usually under the name Gilbert-Varshamov inequality or inequalities. Okay, so this is a classical, this is like, I don't know, 80 years old or something like that. And in the last 80 years, there have been a lot of progress and explicit construction, etc., etc. I will jump right away to the notion of LTC code, locally testable codes. And this is the definition is that you have such a code and there exists an algorithm A, an algorithm such that it's a random algorithm really, given alpha in f2 to the n. Now, let's say it first in simple words. The algorithm, what we want, is that the algorithm will take a vector of size n is very large, right? And it's going to infinity. Will read only bounded number of bits out of the vector and decide whether the vector is inside the code or not. Okay? Well, this is of course impossible. Why? Because to decide if you are code, you know, if you flip a bit outside what you checked, what you read, then it's not, it was in the code, it's not in the code because the code has a good distance, right? It's possible. But, so the most precise is that given alpha in f to the n reads q, so maybe better to write, there exists some q and epsilon, q fixed natural number, q reads q bits, fixed independent of n, and answers and it answer yes if alpha in the code. So it never makes mistakes if alpha in the code. If alpha is not the code, it can make mistakes, but it should detect if alpha is really far from the code. If alpha is close to the code, it may answer yes. So let's write it, and if alpha in code, and know with probability at least epsilon the normalized distance between alpha and the code. Let me explain why this is important even in practice. Let's say that we have an algorithm that can correct if the number of mistakes is 2% or 5% of 10%. Usually you cannot, if the number of mistakes is 40%, there is no chance. If 50, even theoretically it's impossible. But if it's a small amount, now you are getting a vector of size 200,000. That's realistic these days. And we want that the algorithm will read only 70 bits, and will say whether it is close to the code that we can apply the full algorithm to correct it. Right? If not, we will ask repeat again. So we want such an algorithm that will give us with high probability. Now, if you think about it for a minute, you can see that if you have something like that with epsilon positive, by repeating the algorithm several times, but bounded number of times, you can still have it with the probability as high as you want. Think about it. It's a little exercise, but it's easy. So that's kind of, this was kind of a fundamental. It's part of a big subject in computer science, which called testability. That basically the point of this area, I have a huge data. I want to read only very few bits, very few part of the data, and deduce some global information. The question is, are there codes like that? This has been a kind of a basic, quite famous open problem for 3 or 4 decades. Why this was such a difficult problem? Because usually in the area of error correcting codes, just like in much of the many problems in combinatorics, random is the best. You first prove that something exists by random methods, and then you try to have explicit construction, which can be still very difficult. But as they say, in Hebrew is better, you say, if the random satisfy the property, then to find explicit is למצוא שחת בערימת שחת. But if the random does not satisfy it, it is מחט בערימת שחת. And for the English speaker, if the random like that, then to find it is like finding hay in a stack of A. If the random is not like that, then finding an example is like a needle in a stack of hay. Here, random are not LTC. So we are fighting randomness in this instance. Therefore, the community are disputed. Some people believe that such codes don't exist. Sorry. Now, the main problem, one can find codes like that, but not good. So the question is, it's got the nickname C-cube problem. You wanted, people found locally testable codes, but when you read an unbounded number of Q, maybe much less than n, but not bounded, like log n bits. Or they found with a bounded number, but what was not good, the distance or the rate was sublinear. And there were partial results, many partial results. But the CQ problem was, can we find constant rate, that's what they call it, constant distance and constant number of queries. So this was the long-standing problem, and as I said, some people believe it exists, some people believe it did not exist. Interesting phenomena was that there was an intersection between these two sets. One of the big experts in the subject published a book where he conjectured it doesn't exist, and then a few years after, a book which he paper, I don't remember so long, that it does exist. Anyway, the good news is that it does exist. And a few years ago, like 3 years ago, Iri Dinur, Shai Evra, Ron Livnei, and Shachar Moses, and me found such examples, explicit construction, because random or not, of good locally testable code. And amazingly, at the same week, even though it's a kind of long-standing open problem, in the same week another paper was put on the archive by Panteliv and Klatchov from Moscow, who also solved the problem in a positive way. We didn't know about them, they didn't know about us. They came from the area of quantum error correcting codes. They solved some problem there, and they deduced the existence of LTC there. Anyway, turns out there are connections. I don't want to go to that direction. I just mentioned this, that we have error correcting codes here, and we have local testability. That's kind of introduction to relate it to some talk I gave here some time ago. Now, I don't want to talk again about computer science. I want to go to pure mathematics and to talk about two directions of research which kind of were influenced, at least some of it was influenced by that, some of that came parallel to that, and אפשר לעזור? And they're really within pure mathematics. So let me just keep this in mind. I don't have more. Should I write there? I think you can remember this, right? It's not so difficult. I want to write a pure group theoretical result. Now let me write a theorem in group theory. Theorem. This is joint work with Michael Chapman, who's an ex-student of mine. He's now in Princeton. He's coming back to Tel Aviv University. And Iri Dinur. I prove the following theorem in pure group theory, in some sense. There exists some constant C and delta such that for every group G generated by K elements, you have a group, finite, infinite, commutative, not commutative, for every group generated by K element. There exists a subset D in G, in a minute you see subsets of generators, which is slightly bigger. D in G, the size of D, let's call it N, is at most C times K. Maybe I should call this C, not confused with codes. I call it gamma maybe. At most gamma times k. So I enlarge the set a bit such that deleting any delta n of the elements of D still generate. What left still generates G. So now we have a kind of a robust set of generators. If you have a group generated by k element, take the free group on k element. If you delete one element, doesn't. The claim is that you can enlarge the set to n in a linear way, so that now any fraction, even if the enemy will choose, I will say, and delta is independent, the gamma and delta are independent of anything. Just it's an absolute constant for every k. Why we got to this range theorem? We were interested we were motivated by testability kind of question in group theory. I will leave you to think about it and just say that this property is equivalent to every proper subgroup of G, H intersection D is, I always confuse, is at most or at least? H intersection G is at most 1 minus delta n of the size of D. So this really means, assume you have a group, like in the free group it's true, and many groups, that I have kind of an oracle which tells me, given an element in a group and given a subgroup, which is given to me in any way you want, it can decide for you if the element is there or not. And then now I give you a subgroup and I ask you, is this subgroup is equal to the full group or not? And I want you to decide about this question by reading, by applying the algorithm only bounded number of time in a way which is independent of the group and independent of k, etc. Then this gives a solution to such a problem, if you think about it. A probabilistic algorithm which will succeed with a very high probability. And we were interested, we were all, Chapman and I at that time were along the way to another project that I will not talk about. It was the Aldous-Lyon conjecture. Eventually, we wanted to refute this conjecture. We managed, but by completely different methods, so we didn't need this theorem. But still, it was cute. Why it was cute? I mean, it's okay. I see Chen Meiri is here. Where are you? Yeah, I mean, I don't think if I'll tell you this a year or two ago, you find it so interesting, the theorem. Well, it's a theorem, group theory. It's nice that we have very few theorems in groups which are true for every group. In fact, I think Gromov famously once said that a theorem which is true for all groups is either trivial or non-interesting. So this is still a theorem which is true for all groups, and I hope that it's not so trivial. And why this is interesting? Let's apply corollary. Let G now be the group F2 to the K. Okay? Let's apply the theorem to this group. What the theorem says, there exist n elements, n at most constant time t, such that any drop of them still generate. Okay, so we have D inside F2 to the K of size n. Now, for every beta in D, denote the vector, let's call it T of beta, which will be the vector, the inner product of beta with D1, the inner product of beta with D2. I take some order on the elements of D, and I write this. So this is a vector of length n, and that's clearly define a linear map from from G to the to F2 to the N. I claim that this is an injective map. It's an embedding. T is injective. Why? Because if beta is orthogonal to all the generators, then it must be 0, right? So T of beta is never 0.
Beta is in D or in T?
Oh, yes, sorry, you're right. Beta is, no. Beta, no, I don't have C yet. No, beta is, no, you're right. Beta is in F2 to the K. Any vector, you're right, thank you. Any vector in F2 to the K, so this defines an embedding of F2 to the K into F2 to the N. This is a code, right? Let's check the code. So C now, T of F2 to the K is something of dimension K. Okay? Let's see, what is the distance? What is the distance of this code? The distance of the code is, okay, I forgot to say, but it's kind of clear. I define the distance as the minimum distance between two vectors in the code, right? But if it's a linear code, and alpha and beta are inside the code, then the distance between alpha and beta is the same as the distance between alpha minus beta and 0. So the distance of a code is the support of the minimal support of non-zero vectors in the code. Okay, so if we have some, for specific beta, if say I have this T of 0 of B node as a very, I claim that the support is at least delta times n. Why? If not, it means that more than 1 minus delta n of the elements are orthogonal to beta, which means that more than 1 minus delta n of the vectors of D are inside in beta perp. Right? Beta pairs are all the vectors which are orthogonal to beta. They will give me 0, 0. If the number of zeros is more than 1 minus delta n, right, then it means this is a contradiction to the property, because a beta perp is a proper subgroup, and a proper subgroup, subset of the group, subspace, but the subgroup cannot contain more than 1 minus delta n by the theorem, right? So what does it mean? That we have good codes. So this is a proof of Shannon theorem, 80 years after, by a much more complicated proof. But the interesting thing that suddenly we have a Shannon theorem for every group, finite or infinite. For infinite groups, we cannot talk about random group because there is no random model for elements of the free group. What does it mean? Right? So suddenly, I think, I like this theorem a lot, even though I don't know if it's any importance, but I think it's kind of an open and interesting research direction within pure group theory. Built non-commutative, I call it non-commutative error correcting codes. Oh, I'm sorry. No. Apologize. Because suddenly you have some kind of theorem. I tell you what is, I will not talk about, that's not my main, my main part of the lecture, but what I want to show you, that you know, it's almost like Kelev Nashach Adam, you know, the standard thing is to apply math to computer science. But I want to keep in mind that sometimes computer science enriched our pure math world by something like that. It's kind of an open up a direction. What I found the most, you can suggest many problems. I tell you what I found most fascinating, and then I will go to something else. I think that what I'm really interested, and I don't know, I think it's a nice problem to work on, we have the Gilbert-Varshamov inequalities for codes over F2 to the n, right? Now, this is a code. Note, now we have a universal kind of code where if you think about it, you say that the rate is 1 over gamma, and the delta is this delta. But our constant, of course, the sum of them is less than 1. You cannot do better than what you do with this example of F2 to the k. But the question is, can we achieve for general codes, for general groups, what you can get by the Gilbert-Varshamov? Or maybe, which is more likely, that the non-commutativity of the group, the infinity of the group, will enforce some stricter inequalities between RL delta. Here we can say very little. We can say that for nilpotent groups, we can get essentially the same. For some finite solvable group, we got reasonable. Now, what we get in general, the other constant and that's are very bad. But we can prove that for some solvable group, we get some better, but still far from the Gilbert-Varshamov. Anyway, I throw it away, especially if they are young people or if you have some students looking for a research program. I think it's a kind of a lovely, though I don't claim that it's an important subject.
Can you find this D explicitly or efficiently? Or?
Yeah. Yes, we can find C explicitly, we can find the D explicitly. There's no random here, we must do it. Well, at some point in the process, we say, okay, now, just here is an int. It's enough to prove it for the free group on K generator, because then it goes to Z. In some point in this process, we say, let's choose among them in a probabilistic way. So it's semi-probabilistic, but you know, this probabilistic, I think you can even get it by, how you call it, executive search. Yeah, so.
Gamma and delta in the theorem itself, what are they?
Very bad, embarrassingly. So that's why I don't show it.
And you said that these are two constants, but it's not like if you change gamma, make it worse, then you can choose.
No. We don't know to do that. It's not like encoding. No, it's very far. It's a first theorem. I tell you the truth. We are among friends, I can tell you the truth. We thought it's lovely. Okay, let's publish it. And we needed the paper. Maybe it's going to be a surprise for Gil Kalai, so keep it secret. The Israel Journal looked for papers for Gil Kalai's 70th birthday to do a volume for it.
YouTube.
What?
It's on YouTube. This talk.
This talk, okay. That's okay. So we said, okay, you know, this is very nice for Gil Kalai. He's working between math, pure math, and computer science, publish it. And the referee was so excited. I never talked about it before. The referee was so excited. He said, wow, it's unbelievable that 78 years nobody thought about theorem for like non-commutative groups. It probably came from group theory. So he kind of loved it that it's a Shannon theorem for non-commutative group. I don't claim that this is that. Maybe it will lead some insight even for the classical code. Maybe it will open some problems. This is part of the message of my talks here, to see that we should, usually we are mathematicians very proud of ourselves that we contribute so much to computer science. I want us to be a little bit more modest and to see that the computer scientists can also give some insight to us. Okay, now I want to go to a completely different direction, but also inspired by this way of thinking of testability from computer science. And this will lead us to a much deeper mathematics, which I will talk mainly tomorrow, but I want to say something today to give you the spirit somehow of the spirit of my talk. Here is the following problem that you can also think of it as a testability question. I got excited by this when I saw a paper of let's see if I will know to write it. Go on. Arja Sterva and Liviu Pernesco. I hope I'm not making a mistake, which says the following. There exists, for every epsilon, exists delta, depending on epsilon, such that if A and B are permutations in the symmetric group on n elements, now you have to think about n very large, go to infinity, and the theorem is independent of n. That's the whole point of the theorem, independent of n, such that if the distance, I'll explain in a minute, between A, B, and BA is less than delta. Now, what is distance if sigma and tau permutation? Sim n. The distance between tau and sigma is 1 over n, the number of I between 1 to n, such that tau of I is not equal to sigma of I. Right? It's also sometimes called the Hamming distance between permutations. If A and B, the distance between A and B and BA is less than delta, namely they almost commute, right? AB almost equal to BA, then there exist A prime and B prime in sim n, very close. So the distance between A and A prime and the distance between B and B prime is less than epsilon, and they truly commute. They truly commute. Namely, if two percent almost commute and don't commute, what can happen? Maybe you add two commuting matrices, you a little bit disturb them, you do some small deformation, and now they only almost commute. This is the converse theorem. Now, why they interested in this paper? Actually, it's not clear in this that. For them, it was kind of to prove a discrete version of a classical line of research in mathematical physics. Mathematical physics, you can imagine Heisenberg uncertainty, etc. Don't ask me too many questions in this direction because I don't understand the connection to physics. But the mathematics is very simple. There are a lot of papers in the literature asking the following type of problems. You have two matrices which almost commute. Are there nearby commuting matrices? And you can ask it in various ways, in various forms. Some people ask, you have two self-adjoint matrices which almost commute. Are there nearby self-adjoint matrices to unitary? Now, also, what does it mean to be close? If n go to infinity, there are many different metrics on the matrices. Hilbert-Schmidt matrix, operator norm matrix, they're all different. And the answer can be different. It's cute. There in the literature, two papers. One, I think the title, I hope you remember, is more or less like that. Every nearly commuting matrices are near commuting matrices. But there is also a paper which says not every nearly commuting matrices are near commuting matrices. Now, both papers are correct, and there is no fundamental contradiction in mathematics, which still could happen. It's just that they talk about different norms. You see, in the operator norm, there are famous example of Vasilescu, of unitary matrices which almost commute, and they are bounded away from commuting matrices. And there are, in the Hilbert-Schmidt norm, the answer is yes, they are nearby.
In that example, you need to take the dimension to infinity.
The dimension go to infinity, it's very important. Yeah, if you take the same dimension, all matrices are the same, and so it's just a question of epsilon delta. The go dimension to infinity, this is different. And so they proved an analog theorem to that. But do you see a testability question? So this is a testability results.
Sorry, what is the question?
Look at this theorem, and you could see, do you see a testability theorem here inside this? Noga, do you see? Yeah, good. You are trained to that. I look at it. And I was involved in all this testability in computer science, and I saw here testability. Why? What is the testability results? Here is the question. You even can think of it as a code in some sense. Let the code be not linear code. Let be all the be a subset of sim n cross sim n, and you look at the subset inside this product of all A that commute. Okay? Now the theorem, think about it. The theorem tells you the following if you think about it. What is the distance between permutation? Distance small means that they agree on most i's, right? Now I ask you the following question. Give me two permutation A and B. Do they commute? I want you to answer me this question by reading only bounded number of values of A and B. Okay? The theorem says, yes, there is an algorithm to do that. Pick up a random I between 1 to n. If they commute, then ABI equal to BAI, right? But if they don't, even if they don't, with high probability, if you will get yes, that AB, with high probability that ABI equal to BAI for 70 i's, then it means that on almost all they commute, right? If they almost all commute, according to this theorem, they are very near the code. They are nearby the code. This is exactly testability results. It says that this is a locally testable code in the non-commutative sense.
But don't you need epsilon to be phrased in terms of delta?
Yeah, you can do. A student, some student of mine and other work on this problem and express epsilon delta, but at this point we are only talking about that. In this case, but let's continue further. Okay, now I'll give you another equation. They were interested in that equation just because they wanted to do some kind of a discrete mathematical physics. I'll give you another equation. What about the following equations? A squared b, say, equal b cube a. Assume you have a and b, such that the distance between a squared b and b cube a is close to 0. It's very small. Are there nearby a and b which almost commute? Which do satisfy the equation? This is kind of a very natural problem in many areas of mathematics. I have an almost solution, and whether an almost solution is really nearby a true solution, and it's just a little bit of experimental mistake. Right? What do you think about this equation, for example? Let's make a vote. Who thinks this equation? We call it equation is called. No, now I'm talking about the symmetric group. I have the norm, I have the metric.
Yes.
You think yes. We call it, equation is called stable if every almost solution is nearby a solution. This is stable or not? Who thinks it's stable? Who thinks it's not stable? One, okay. Now the answer is non-stable. I don't know to prove it directly. Here is the story. Here is a little lemma. Here is a little lemma which says the following. Now we can ask the following. You know, we mathematicians, what we know the best is to generalize, right? So why to look just like here, instead of one equation, why not to look in another equation? Let's look in a system of equations. Okay? I take W to be some system of equations, but you know, I can always pull the equation to one side, right? And think of it instead of a squared b equal b cubed a, let's think of it as a to the minus 1, b to the minus 3, a squared b. Okay? Equal 1. It's the same thing, right? But now think of this as an element in the free group on two generators A and B. So if I have a system of equations, I can think of W as a R1 from RL, a subset of the free group on x1 up to xd. Doesn't have to be two generators. So they have D generators, L equations, and ask whether the system is stable, namely whether every almost solution in the permutation group is near a solution. We say that the system is stable if this is the case. Okay? And now here is a lemma, which is very simple, but is extremely important. Third, the stability of W in permutation, yeah, right, in Sn. Later on we'll talk about other. Does not depend on W, depends only on the quotient group Fx divided by the normal closure of W. We can look at the group generated by the D generators and adding the L relation, and we get a finitely presented group. Okay? Now I claim that the answer of the stability of W depends only on the group and not to W. What does it mean? It means that if the same group will have another presentation, maybe even with a different number of generators, and a completely different relations, you know that to present a group by generator relations, there are many different ways to do it. Now the stability depends only on the group and not on the presentation, which means that now I can define the notion of a stable group, right? And now I'm talking with respect to permutation with the Hamming distance. Tomorrow, the norm on the permutation is always the Hamming distance for every n. And I want, and when I say that the system is stable, means for every epsilon there exists a delta, so that each day you have an almost delta. If the equation are delta satisfied, then there is a solution which is epsilon quad. Now, you are right in the following sense, that if I take another presentation for the same group, the relation between the delta and W can be different. But still, there is epsilon and delta. Okay, so the stability is independent of the presentation, depend only on the group. So which gives us a notion of stable group. If you think about it, it's very similar to what happened in Galois theory. In Galois theory, we have system of equation, or we have a polynomial. We ask, is the polynomial is solvable by radical? We associate a group with a polynomial, the so-called the Galois group of the polynomial, and we say the polynomial is solvable if and only if the group is solvable. That's why we call it solvable group these days, right? So now we say the equations are stable, the system, if and only if the group is stable. But here the analogy stops. Because in a Galois, once you say solvable, to check if a group is solvable, we know. The group is stable. Up to now, it's just a name, right? But it promotes the idea to look for condition about groups to be stable or non-stable. Now, what happened in the examples I gave you? In the example of the commuting matrices, the group is simply, right, you take two generators and they commute with each other. The group generated by them, the group presented by them, sorry, is the abelian group, Z cross Z, right? In the other case, with the other equation, the group generated is a famous group. It's called the Baumschlag-Solitar group 2,3. Baumschlag-Solitar, BS. And I don't know the only way I know to prove that the equations are not stable, not because I know to present explicit example, because nowadays we have conditions to check, not always, but in some cases, we know to check whether a group is stable or not. Not in all cases, very far from knowing it, very far from knowing it in all cases. But in the last couple of years, the theory was kind of an exponentially grow. And there is kind of suddenly many people got into this. I just throw some theorems for those who know the words, because I don't want to start to explain. We have a theorem of the following kind. Assume gamma. So now it's a question about gamma. Forget about the equations. We have to check whether a group gamma is stable or not. Here is a crazy condition. Assume gamma is a amenable group. Some of you may know what it means. It's kind of the opposite than expanders. Assume gamma is an amenable group, then gamma is stable in permutations if and only if the finite index IRSs of gamma are dense in the space of IRSs. IRSs of a group are something which is called invariant random subgroups. Invariant random subgroups is kind of an interesting subject in a dynamic ergodic theory about random subgroups of a group. The space of invariant random subgroups is a topological space associated with every group gamma. And the criterion for stability, kind of out of the blue, it's not so much of the blue, it depends on some work of Orenstein and Weiss about amenable group. The claim is that a group is stable if and only if those specific class of finite index subgroups, those which are the simplest type of that, are dense in the IRSs. The Aldous-Lyon conjecture, by the way, that I mentioned before, it was the conjecture that those finite index IRSs are dense in the IRSs of the free group. We prove that they are not. But this is not a contradiction theorem. The free group is clearly stable, right? Because there are no equations. No equation means that it's stable. But the theorem is really for amenable group, not for other groups. Now, this theorem about amenable group is a joint work with Oren Becker and Andreas Thom, solved many problems, like every abelian groups, every nilpotent groups, not every solvable group. Some solvable groups are stable and some solvable groups are not stable. But the Baumschlag solitary group, by the way, which is not amenable, but is residually amenable, so we can still apply it to this case to show that it's not stable, but we don't know. I cannot give you example. You see, if it's not stable, it means that there exists a sequence of permutation when n goes to infinity, an, bn, such that the equation an square equal bn, an square times bn is almost equal to b cube times a, which almost this, and it's not close. I don't know.
So you also write two papers.
What?
You can write two papers, nearly satisfiable.
No, so it really opens a lot of questions that one can talk about that. For example, if you go to the groups with Kashdam property T, then Oren Becker and I proved that, let's say, if they are residually finite, let's say if they are linear, they are never stable. But there might be, which it's an open problem, we maybe mention it again in the lecture, maybe flexible stable, which is another notion. So over the years, we started to develop techniques and methods in pure group theory to answer this. I think I'll finish here because everyone wants to eat, me included. and I will push this direction tomorrow because I will show you that stability of groups might be a method to solve some of the most outstanding problem in modern geometric group theory, whether every group is sophic and whether every group is hyperlinear. These are very famous problems which have have not been solved yet. So don't hold your breath, I'm not going. On the other hand, we solve a good number of related problems, and it looks like maybe we are close. And I will relate all this to high-dimensional expanders tomorrow. This will come up tomorrow. Okay, just on time and 5 seconds to finish. Thank you very much.